Good morning, Astronomy 1010. This is our final lecture today, the 13th lecture in our journey through the solar system. Today we cover an exciting topic. We'll end on an exciting topic, which is the Jovian Moons. Lots of fun pictures to show you today if everything works out correctly. Let's do a bit of administrative stuff since it's the final class. A couple of announcements. The first is, and I want to say this before I forget, don't forget to do your course evaluations and fill out your student ratings of instructions, or SRIs. Normally, I hand out the students paper ones and I sort of sit there and force you to do it. But I can't do that anymore. So it'll be up to you if you'd like to, rate the course or whatever. You can, let's share my computer screen here. You can go to CCRI and go to the My CCRI page. Let's see here, My CCRI. Now, I'm not 100% sure where it is for you guys, but I suspect you'd want to click the For Students tab. I usually click the For Faculty tab because that's where I'm at. And I can go down here and look up my student ratings of instruction. I noticed that last semester, spring semester, most people did not fill them out. So I think I had like one review. I may not have been as vocal last time as saying, hey, don't forget to go out and fill out a course evaluation if you'd like. So I encourage you to do that if you'd like. The other thing is the exam, which it seems like no one wants to take. And that would have been like next Monday or next Tuesday. I don't know if there's supposed to be a reading day. But as you know, and I'd like to just say it again because people tend to miss details, that anyone who wishes to not take the final exam can substitute the grade that they got for their midterm in place of it. So if you got a 62% on your midterm and that's working for you, you can take a 62% for your final and not have to take it. I'm assuming nobody wants to take it because I haven't heard anyone say I'm dying to do this. If you are dying to do this, I need to know by Friday. Today would be better, but Friday the latest. I'd also like to say that I did catch up on all the grading. I did that last night. So everything is graded up to now. This week's lab homework combo was the massive Jupiter lab, which we did on Monday. And today we'll be doing our final homework number 11 on the Jovian Moons. I definitely need that stuff by Saturday at the latest. I'm gonna give you Saturday because that's been the tradition so far. But on Sunday, I'm grading and that's it. Like, that's the end of the class. So if you didn't get it in by then it's just not gonna work, okay? Obviously, you've only got 2 more places to earn some points, which was the lab on Monday and today's homework. So since we don't have to do an exam, we might as well finish this out right. We're going to do it together. You can make sure it gets done correctly, and we'll have as much fun as we can. But once again, the deadline for this week's work is Saturday. After Saturday, I'm closing out the books. Does anyone have any questions or things they want to ask me that I didn't make clear enough? Okay. Well, then it seems pretty straightforward. Let's talk about Jovian moons. There are a lot of Jovian moons. I think Jupiter has maybe 65 and Saturn even has a few more than that. So we won't be able to talk about all of them. We're going to focus on the really big moons that have interesting geology. Just as a point of curiosity, do any of you cats out there know what the biggest moon in the entire solar system is? If you had to guess, what's the biggest moon in our solar system?
Is it Io?
Io is one of the bigger ones, but it is not the biggest. For comparison, that sounded like
First moon.
That sounded like Jake.
Yeah.
Io is, no, so that's what I was about to, whoever said that, Io is roughly the same size as Earth's moon. So Io and Earth's moon are about the same size, but there's at least 3 or 4 that are bigger. Maybe I'll help you cheat.
Is it one of Saturn's?
It's one of Jupiter's.
Titan?
Not Titan. Titan is like the 3rd biggest. So Titan's close, but not quite there. I have a little overview of Jovian Moons, a crummy little slide that I can show you guys. And this is just to show you, this is not all of the moons, excuse me, but it's a handful of them. Let's see if I give you a cheat sheet, if you can figure it out. F559. And I'd like to show you that these are the moons in comparison to 3 objects that you're a bit more familiar with: Mercury, the Moon, and Pluto.
Looks like Ganymede.
Yeah, Ganymede. Ganymede's the largest moon in our system. Did you guys know that I think it's 3 moons in our solar system? Ganymede, Callisto, and Titan are all bigger than the planet Mercury? Isn't that wild? Now, think about that. What's the difference between a moon and a planet anyways? Actually, suppose that's a serious question. What's the difference between a moon and a planet?
They have to have an atmosphere in order to be a planet.
No, Mercury doesn't have an atmosphere and it's a planet.
A core.
Has to have its own orbit.
So, yeah, that's it. It's about whether it's orbiting the sun or whether it's orbiting a planet. Ganymede, Callisto, and Titan are not considered planets for no other reason than they primarily orbit around another planet. Mercury orbits around the sun. Therefore, it's a planet. Titan, Ganymede, Callisto orbit around Jupiter or Saturn. Therefore, they're moons. But it's really kind of arbitrary when you think about it. If Ganymede, Callisto, or Titan orbited the sun, they would be planets. And they'd be big enough and strong enough probably to clear out their own orbits. So suppose I ask you guys another question, and this is the real thing here. If the largest of the moons are just a bit bigger than Mercury, what is the dominant form of geology on Mercury? You guys know your 4 geological processes, right? These are the kind of questions I'd be asking on a test. What's the dominant form of geology? Pardon?
Volcanism.
False. There are no volcanoes on Mercury. Wow. Maybe we need to look at a picture of Mercury. I'm starting to get the heebie-jeebies here. Maybe we didn't spend enough time looking at
Is
Mercury.
it erosion?
Mercury has no atmosphere. So erosion takes the form of wind, water, and ice.
Solar wind?
The solar wind isn't a type of geology, although it is an important process.
Well, according to my notes, the 4 geological processes are impact cratering, volcanism, plate tectonics, and erosion.
So why don't you look at this image of Mercury and tell me which is the dominant form of geology?
Impacts cratering.
Yeah, you can see it. It's all beat to hell with impacts. That's it. It's an airless world, no atmosphere, and it's just beat to hell with impact craters. Now, it does have another slight form of geology. Can you guys see these long stripes that go across the surface? I don't know if we ever talked about this. Although you're looking over a huge range here. These things that look like long stripes on the surface are actually huge cliff walls. The name that we give them, they're called scarps. I don't know if I ever told you that. But a long cliff wall is called an escarpment, or sometimes we just call them scarps. And famously, besides impact cratering, the only other type of geology that Mercury has are these legendary scarps. And you can see they kind of cut through craters in different places. let me, I didn't think I was going to need this today, but let me, excuse me, let me call up one of those slideshows here. Okay, open file location, Planetary Geology. And I want to, I think I remember asking this question, but maybe it was in the summertime I asked it. So here's a couple of pictures of Mercury, and I want to show you this one in particular, slide 97. You can see here one of the legendary scarps on the planet Mercury, these long cliff walls. It might not look like more than a little lump or a ridge to you, but if you were in your astronaut suit standing next to this thing, it would seem like you were standing at the edge of the Grand Canyon. This would be a massive cliff that could be 2 or 3 kilometers in height, which is pretty intense, right? So you can see the cliff wall passing through the center of the crater here. Can you tell me which came first? Which came first and which came second? The cliff wall or the crater? Which is older? I'm hoping you can use your Sherlock Holmes deductive reasoning there, or is it inductive reasoning? I think it's deductive reasoning.
You can hear me, but I think the crater is older.
Okay, Andrew, how'd you know that?
Well, you can see it looks like some form of erosion, or just kind of, this crater just looks like a scar. It looks like if that's a fault line, or
you could consider that a type of, that cliff is a type of fault. But I want to correct you on erosion. There's no atmosphere on Mercury. Erosion can be wind, water, and ice. There's no wind, there's no water, and there's no ice. So erosion's not really an option. I was thinking of something simpler.
So I guess through plate tectonics, it's altered that that crater.
Right. So how would this look different if the crater was younger? If the crater came after the cliff wall, how would things be different?
Perfect.
What do you mean by perfect? Sorry.
Fresh, brand new. It would look like the one that's on the lower left to it, or the one that's just above it.
Yeah. Okay.
The escarpment line wouldn't be going through the crater.
Thank you. I was just hoping for this really simple thing. If the crater came after, it would have beat the shit out of that cliff wall, and it wouldn't be there cutting through the crater, right? The cliff wall would have been annihilated and destroyed. That was the simple answer I was looking for. And so you weren't wrong. It would look more like this. But the fact that you can see the cliff contiguously moving through the crater tells you that the cliff comes earlier. So if most of this cratering activity took place during the heavy bombardment period, then Mercury's had some other form of geology that affected it. And that geology, since it takes the form of a cliff wall, seems to be related to plate tectonics in some way. In fact, we don't just see these cliff walls in a few places, we see them all the hell over Mercury. A planetary-wide image will show these. You can see all the stripes here moving across those. All of those stripes that you see are all cliff walls. They're not just like in one location, they're covering the planet. Does anyone know how Mercury got these? You'll remember that Mercury has a larger than average metal core. Compared to the other terrestrial planets, a greater fraction of its interior is in the form of an iron core than the silicate rock on the outside. And you guys know what happens to metal when it gets cold and then it gets hot again, right? It contracts and expands. Mercury would have started off warm, and you know that small planets cool rapidly. Well, the core, being made of metal, would contract by a greater amount than the outer silicate rock layers. And the outer silicate rock layers would find themselves falling and collapsing onto a shrunken core, and it creates these folds, which are something like tectonics. They're tectonic in nature because it involves the lithosphere cracking and pushing against itself. And these folds would have formed the cliff walls that you see all over Mercury. They're kind of like stretch marks, but they're actually more like shrink marks, right? They're shrink marks. Now, I have a point that I'm trying to make here, believe it or not. And my point is, if Mercury is roughly the size of the biggest moons in our solar system, and the only real type of geology we see on it is cratering with a little bit of stretch marks, all right? So cratering with a little dash of tectonics, then you would anticipate that the types of geology you would find on the moons of the Jovian planets to be what? What are you going to expect to be the types of geology you would find? I mean, what property of a planet affects the amount of geology that you see on its surface? What are the fundamental planetary properties that affects the amount of geology a planet develops? They might be in your notes as the 3 fundamental properties of a planet. Sorry, Andrew, you're a little cut out there.
Size.
Can you say it one more time? Because I couldn't hear you.
Size.
Size.
Like the size of the planet?
Yes.
How fast it rotates.
Rotation definitely affects erosion and distance from the sun. It's size, distance from the sun, rotation. But size is probably the most important to determine whether or not you're going to have volcanism in an atmosphere and stuff, right? So what might we conclude? Now, see if you can come around to my point, to my way of thinking. In a way, I'm trying to lead you on this sort of garden path here, but I'd like you to just play along with me. In this picture, you can see that even the, what was that? Shoot, I just forgot the damn slide number. 59. In this picture, you can see that there are moons of different sizes, but the very, very biggest moons, the ones with the most size, including this one and this one, are either the size of the moon or maybe the size of Mercury. So based on the fact that planetary size is one of the most important properties that determine the amount of geology you have, what would you guys predict to be the dominant mode of geology on these large Jovian moons?
Cratering.
Yeah, you'd expect them to be beat up pieces of crap that are just covered in craters and nothing else. And you know
You can
what?
kind of see it in all of them except for Titan, because
Well, hold on, Joel. It turns out that it would be a very reasonable thing to assume that all of the moons, being small, would lack interesting geology and therefore would just be beat up balls of cratering, which, yes, Joel, some are, but not all of them. It turns out you would be wrong to predict that because you've forgotten about one important thing, and that is the frost line. Remind me again about the frost line. What does that mean? We've spent some time talking about it. Oh, goodness God. Can someone tell me about the frost line? I might as well just give up if you can't tell me about the frost line.
freezing point.
Okay, there's a little more to that, Joel.
With water, like the water freezes and it turns into this gas at
Well,
a really
If water
cold
freezes, it doesn't
temperature.
turn into a gas. You got to clean up your speech.
It's like it kind of like evaporates. It's like evaporated
We
cold
call it
water.
sublimation. In space, sublimation is solid to gas. You can't have liquids in space.
Oh, so it'd be like it's like ice particles.
Okay, where are the ice particles?
It's in space because everything's really cold in space. So
Not true. If you're in space and you're near the sun, everything is really hot. Things
well,
can be hot or cold in space depending on how far from the sun you
well,
are.
like near the ice giants, like Neptune and
It's 3 AU away
Okay,
That's
so
the
from the
asteroid
sun.
belt.
okay,
From the sun.
if I was a little kid and I said, "What's the idea behind the frost line?" None of you would have explained it to me yet. I want to know what the concept is. Yes, it is 3 AU from the sun. What happens at 3 AU? What changes?
Hydrogen ice transforms
Whoa, whoa, whoa,
into.
whoa. Okay, yes, hydrogen ice. Let's just talk water for a second. Let's call this the H2O frost line. H2O is a hydrogen ice, but it's in particular water. But anyways, Jake, keep going. Wait, hold on. Hold on, Brendan. Hydrogen cannot turn to ice. Let's just get this clear. This is a molecule of water, H2O, and then this is like hydrogen, like a diatomic hydrogen atom or molecule. Hydrogen is not the same thing as water. Can we all agree on that? Water might have two hydrogens stuck to it, but water is two hydrogens and one oxygen atom. So you can't say hydrogen turns to ice because that doesn't make no sense to me. Do you see what I'm saying? You need to clean up your speech some more. But anyways, Brendan, if you could just talk about water instead of hydrogen, or Jake, if you want to try it again, whoever wants to try it, what's happening here?
So hydrogen ices are transforming from vapor into solid ice grains.
Very good. So here the water is in a gas or a vapor form, and here it's in the form of ice pellets, right? That means the only thing you can make a planet out of interior to the frost line is rock and metal. And therefore, all of your planetary geology will be based on cracks and warming of rock and metal. But guess what? Out here, beyond the frost line, you can form moons of ice, rock, and metal. And because ice has a lower melting point or a lower, the lower melting point than rock and metal, and because it's more brittle than rock and metal, you can form cracks in the ice, and you can form geology with ice that's like a bizarro, weirdo version of the normal terrestrial geology we've studied so far. In other words, whereas over here you have things like volcanism, and you have plate tectonics or something, here we see a shadow version of them. And out here, instead of volcanism, we get volcanoes. Volcanoes that spew water instead of molten rock. And we have ice tectonics. Instead of needing to form cracks in a rocky surface, you can break the ice apart. And that means all of this really cool active geology is possible. And it's kind of like weirdly related to the geology we've studied so far. I mean, could you imagine being on one of these icy moons surrounding Saturn and watching a cryovolcano spew shards of ice up into the outer space environment? You would think that you were in some crystal energy forest from a science fiction movie. Like, let's rely on our weed smoking artist friends to help us envision what a cryovolcano might look like. There's a couple of space art things that I dig. This is one that kind of appeals to me for some reason. Imagine if you could take a walk in your spacesuit and watch a water volcano spewing vapor that's immediately condensing into ice grains as you see the rings of Saturn. That would probably be a pretty beautiful sight, right? It would probably be wild to look at that. And in fact, just because you guys know I'm a big sci-fi fan, there's a kind of cool movie, if you've never seen it before, I may have told you before, and I'll make reference to it. It's about a hypothetical first manned mission to the moon Europa, which we're going to talk about today. And what's really cool about this sci-fi movie, The Europa Report, it's kind of like, remember Blair Witch, how the whole movie is told from a point of view cam? This is like 2001 meets Blair Witch. The movie is fiction, but it tries to present itself as like a fake documentary where you're watching the astronauts going to Europa in their craft. And it's actually really scary, but also beautiful and profound because all of the science that's in the movie is 100% legit and realistic, and it completely dovetails with stuff that we talked about in this class. Also, this movie's kind of scary. It gave me the willies. So bust out the anchovies pizza special with the beer and put the kids to bed and be prepared to see just how scary science can be. Okay, it's really, really fun. I recommend this as a kind of closing fun chapter to our class. Anyways, the point is this: outside the frost line, you're going to see that these moons are capable of all kinds of interesting geology. So they're a laboratory where we can continue to study these cool geological processes. Let's take some notes about a top-down view of moons. I tend to think there are sort of three categories of moon. You got your big fat moon, which is going to have all kinds of cool geology on it. You get your medium-sized moons, which can have a little bit of geology. And then you get your little dinky moons, which are beat up balls of ice, basically asteroids covered in ice. And let's just take a quick note on that, because I think this is an important concept. We're going to focus on mostly the big moons and a couple of the more interesting medium-sized moons. So there are three classes of moon. The most interesting, of course, would be the large moon. A large moon is something that has a radius or a diameter that's greater than about 1,000 kilometers or so. And when you're this large, you are definitely going to be spherical in shape. So self-gravity will deform you into a sphere. And they're going to have several types of what I would call interesting geology. So several different types of interesting geology. I don't know if you guys know what I mean by interesting, but remember, in the four geological processes, impact cratering is one of the four types of geology. But because impact cratering is what you get by default, I don't consider impact cratering interesting geology. I consider ice tectonics, cryovolcanoes, and erosional things to be interesting. If you're just a beat up ball of craters, you're kind of not as interesting, geologically speaking. So you'll see several different types of geology. And another thing about your typical large moon is they maybe even an atmosphere. So as Joel pointed out, the moon Titan has a substantial atmosphere, and a couple of the others have a little baby atmosphere, just almost a thin sheet of gas around them. So large moons tend to be where it's at. Then something that's also interesting is your medium-sized moon. Your medium moon is just barely capable of becoming a sphere. One good rule of thumb that I've learned in my science courses is that any lump of matter, any lump of rock that's greater than 500 kilometers will self-deform into a sphere under its own gravity. So that's the cutoff right there. If you hit the 500 kilometer mark, gravity will just uniformly mush you into a sphere. Under this, you can be potato shaped, but over this, you're going to be a sphere. So yes, it will be a sphere. It usually won't have several types of interesting geology, but oftentimes medium moons will surprise you. They'll have one interesting geological feature, just one thing that makes it tick, you know? So usually there's kind of, see here, one interesting geological feature that's different than just simple craters. And I'll show you examples of that in a moment. They often do feature some cratering too. So usually it'll be a blend of cratering and one interesting geological feature. And then you've got your most common type of moon, what I would call your dirtbag moon, just your run-of-the-mill garden variety asteroid or ice pellet that's been kicking around for a long time in the solar system, getting stoned, so to speak, okay, by impact craters. Okay, so this is your small moon. And your small moon will be some kind of a lump that has impact craters on it. So no cool geology. I mean, sometimes they'll have an interesting feature or two, but you won't see like cryovolcanoes on a small moon. And there'll be lots of craters. And small moons have a diameter that's usually less than 500 kilometers. Because I'm going to talk more about the large moons and about the medium-sized moons, let me just start by showing you an example of a small moon so that you kind of get where I'm coming from. But first, let me sip my seltzer and give Andrew a chance to catch up here. Andy, let me know when you're done getting all this stuff down.
All right.
And I'll have a refreshing, delicious sip of polar seltzer.
Not sponsored.
Yeah, I wish Polar Seltzer would sponsor me. That would be great. Then I wouldn't have to go to Job Lot to buy them. Maybe I should. I could have product placements in my astronomy class. I could get like Riccati's, and they'd all be Rhode Island specific stuff, like Riccati's grinders and New York System hot wieners.
All right, I'm all set.
Okay, cool. So because we're not going to do the small moon thing too much, let me just show you some a cool photo. I think I showed you this moon before, so I should try to pick a different one. But Phoebe, O-E-B, Phoebe, the moon, is a moon of Saturn. And the Cassini spacecraft, you guys remember Cassini was the mission that we sent to Saturn, got some nice up-close images of it. And this is an example of your small dirtbag moon. I mean, look at all the impact craters on it. I think that this impact, whatever made this big gouge out of its surface, that probably came close to having enough kinetic energy to shatter and fracture the moon apart into splinters. And we do know that happens from time to time. So there was a lot of violence done to this thing over the years. I bet, I can't remember the exact dimensions of this, but it's definitely going to be under 500 kilometers and actually might be quite small. The mean radius of the thing is about 100 kilometers. So you can see 200 kilometers across is exactly what I'm talking about. I wonder if they have its density here, because the density would tell us some things, right? Okay, guys, if the density is 1.6 grams per cubic centimeter, what does that mean to you? Let's see what you've learned in my class. I'm telling you the density is 1.6 grams per cubic centimeter.
More than water? Well, 1.6 more than water.
It's okay, it's more than water, but not by a lot. In other words, the density is your usual your first guess at what the composition will be made out of. So if you have a density of 1.6, see, that means something to me, and I want to know if it means something to you. If your little small moon has a density of 1.6 grams per cubic centimeter, then I already know what that thing is made out of. Do you? Oh, crap. Guys, go back and look at your table of common densities, please. I would have asked you like 10 questions about density on the exam. It's a good thing we're not taking that.
1 gram is H ices, and then 3 grams is rock. So a bunch of H ices and some rock mixed in.
That's right. I would say it's ice and rock. I know based on the density that this is a chunk of icy, rocky bits. And in fact, you can see in the Wikipedia article there they're sort of confirming that as much. And I hadn't read this before, or maybe not in a long time. Where is it here? I just saw something. Images from the Cassini spacecraft indicate that Phoebe's craters show considerable variation in brightness, indicating the presence of large quantities of ice below a thin blanket of dark surface deposits. In other words, rock and ice. And we didn't have to read the article because we know densities, and density tells you chemical composition. With that in mind, let's look at these big moons, some of the interesting ones, and let's keep track of their density as we look at their interesting geological properties. So here are the moons I'd like to try to cover today. I'm going to erase. Basically, I want to show you guys all kinds of awesome pictures today, but I want you to take away what you've learned in this class. Is I'm hoping that in the future, when you see a cool planet or a moon or something, you're going to be thinking in your head, what kind of geology is that? What's the story here? What happened to this thing? So we've got our 4 planets here. Jupiter, Saturn, Uranus, and Neptune. And I would consider the absolute most important moons for us to talk about. Around Jupiter, they're the so-called 4 Galilean moons, the really big ones that Galileo first observed. Io, Europa, Ganymede, and Callisto. Did I spell that right? It looks weird. Callisto. Around Saturn, the biggest moon is Titan. That's the only moon to have a really substantial atmosphere, so we definitely want to talk about that. But Saturn has some medium-sized moons that are really worth talking about, like Enceladus and, oh my gosh, why am I blanking on this moon here? I'm having sort of like a brain aneurysm. Iapetus, or Iapetus, I don't know how to pronounce it. Sorry, I lost you guys. There you are. Iapetus is really worth taking a peek at. These are medium-sized moons, but they're still really cool. It turns out that all of the moons of Uranus are all medium-sized moons. So I'll probably spend the least amount of time talking about them. But here's something interesting. Whereas most planets and moons are named after Greek and Roman mythological creatures, and that's just a tradition that stretches back hundreds of years, the International Astronomical Union broke that tradition with the moons of Uranus, and they're all named after Shakespearean characters. So the names of the moons of Uranus are like Oberon and Ariel and Titan and all these different things. The medium-sized moons of Uranus are really cool, but we only have photographs of them from the Voyager missions. So they tend to be black and white images that are a bit grainy and, you know, not up to our modern digital imaging standards. So each one probably has its own you know, Wikipedia page, but I thought maybe I could just show a few of them here. Wait a minute. They have Io in there. I don't like this. Well, let's try Titania. Actually, you can see there's kind of really intense geological scarring on these things. They're all very, very low-grade images here. You can see they're covered in impact craters. Man, this looks pretty wild here. If you had to guess what type of geology this was, what would you say this is?
Tectonics. They look like scarps.
Yeah, they look like giant scarps and grooves. Something happened to the ice here, probably some massive geological stresses. You know, there's one really legendary moon of Uranus, and it's called Miranda. And I want to show you this picture because the first time I saw this, I just couldn't make heads or tails out of what was going on here until I read something really interesting about it. What would you guys say is the deal with this thing here? Look at this thing. It's crazy. There's some craters, but it's not uniformly cratered.
It almost looks like somebody made it out of clay.
Yeah, right? Now, these definitely look tectonic in origin. We would think of these cracks as tectonics. They're certainly not volcanoes. They're not craters and they're not erosion, but I thought, well, these must be some wild ice tectonics, but the fact that they cover the surface in such a weird way. One, I believe the leading theory of what happened to this moon is they think this moon underwent such a powerful collision that basically something smashed this moon and broke it into a bunch of shards, and then the shards awkwardly glued themselves back together through gravity. So basically, you're looking at the planetary equivalent of a broken vase that has been very badly glued back together. So basically, this entire moon got shattered into fragments that then recollapsed on themselves. Totally wild. So this might be ice tectonics, but so this is a medium-sized moon. And this kind of fits our definition of what happens on a medium-sized moon. You get craters, but then you get this one really wild, interesting type of geology. Just for fun, I was hoping to see the dimensions of Miranda. I know the dimensions of many moons, but this one isn't one that I remember. So if the radius is 235 kilometers, its diameter is just over the line for 500 kilometers, right? So this thing is just barely spherical. Okay, cool. So the one big moon from Neptune, so basically, I'm not going to spend a lot of time. I was trying to say that I'm not going to talk about the moons of Uranus, and there I went talking about the moons of Uranus. So I'm lying as usual, okay? There's a beautiful large moon of Neptune called Triton. Try not to confuse Titan, moon of Saturn, with Triton, moon of Neptune. And then if there's time at the end, I'd even like to say a few words about Pluto. Because in a way, Pluto actually has a lot in common psychologically with some of the large and medium-sized moons of the Jovians. Let's start by talking about these bad boys right here, okay? Jupiter is a hell of a planet. It's 1,000th the mass of the sun, but it's 100th the minimum mass necessary to become a star. In some ways, you could think of Jupiter as a failed star, and in astronomy, we have a name for failed stars. We call them brown dwarfs. So it's important to think of Jupiter as something that we would consider in astrophysics a brown dwarf. Is an object that forms from hydrogen and helium gas, but barely missed the threshold of the minimum mass needed for fusion. So a brown dwarf is like a star with no fusion or a failed star. Why am I mentioning this? Because it's important to understand that in the Jovian system, Jupiter and its moons kind of constitute a little mini solar system unto themselves. And they have a very similar kind of psychology to the solar system, where there's a difference in the type of geology you see on the moons based on how close they are to Jupiter. Just like Mercury and Venus are the hottest planets And then as you get further from the sun, the planets sort of change their characteristics. So too do the moons change their characteristics as a function of their distance from Jupiter. Also, remember that at 5 AU, so let's look at the distances here, because I think the distances really matter. Jupiter is 5 AU, Saturn is 10 AU, Uranus is 20 AU, Neptune is 30 AU, and Pluto is 40 AU from the sun. Nice, easy to remember numbers, 5, 10, 20, 30, 40. They're so close to evenness that people have remarked over time that maybe there's some kind of magic about where planets form in a solar system, but those theories never really went anywhere. It just so happens that there's nice, easy to remember distances for these planets. Now, at 5 astronomical units, Jupiter is just barely past the frost line. And that means whereas many of these moons are extremely icy, half and half ice and rock, the moons of Jupiter, although they do have a lot of ice, are much more on the rocky side. And let's start by taking a look at probably what's one of the most interesting moons in our solar system. That's Io, legendary moon of Jupiter. And feast your eyes on this bad boy right here. It kind of looks like a pizza. It's, well, I don't know if you guys know about this. I heard someone mention Io in the background earlier today. Do you guys know what's going on here geologically? Let me ask a really simple question that I think any one of you should be able to answer. Is this a young or an old geological surface?
Young?
Excellent. Was that Mateus?
Yeah, that's me.
Oh, are you trolling again? Okay. Mateus, how'd you know that?
I hurt my finger pretty badly, so I keep having to get up and like put ice on it.
You hurt
Because
your finger.
it doesn't have a lot of impact craters.
That's exactly right, my friend. I was hope that's what I wanted to hear. Our number one criteria for whether a surface is young or old is how many craters do you have? And this appears to have 0. So it's an extremely young surface. Maybe one of the youngest surfaces in our solar system. Do you guys know what's going on here? Does anyone know the story behind this thing? Okay. Io is the most volcanically active moon. Sorry, I have this sensitive trigger finger on my mouse here, and I think it was 62. Io is the most volcanically active moon in the entire solar system. More volcanoes go off on Io every day than go off on Earth. And there's volcanoes going off every day on Earth. Each one of the black pits that you see on the surface is an active volcano actively spewing out sulfur dioxide and CO2 and frost. And in fact, it is so volcanically active that during the Galileo mission, we actually got direct imaging of active volcanoes blasting frost up into the sky. You would think that with so many volcanoes going off, and by the way, this thing is basically the exact same size as our own moon. Our own moon does not have all this volcanism. It's just a lump of rock with with craters on it. And maybe some Maria, okay? But it's nowhere near this level of volcanism. How can this thing be so volcanically active? We'll get to that in a second. But I want you to see that all of those yellow streaks that you see are all frozen sulfur dioxide compounds. As soon as they get blasted into the icy vacuum surrounding Jupiter, they turn to frost crystals and rain down onto the surface. I'd like you to compare these big streaks of yellow with something that you might see in Yellowstone. Let's look at the Grand, has anyone ever heard of the Grand Prismatic Spring in the Yellowstone Caldera? It's one of these sort of legendary places to visit in the United States, just for its natural beauty. It's a sort of hot spring geyser caldera, And can you guys see those yellow and orange streaks surrounding this? It's sort of the same kind of sulfur dioxide compounds, or similar to what you're seeing over here on Io. So here's an image of the active volcanism going off, and I think there's another one here too. A question that you might have is, okay, Brendan, so the first question is, why so many volcanoes? Shouldn't this be a small rock that cooled very quickly? The smaller your planet, the faster it cools off. It turns out that being close to Jupiter itself provides a mechanism for internal heating. And that mechanism is known as tidal friction. Because you have something the size of the moon sitting the same distance away from Jupiter, Jupiter has 1,000 times more mass than Earth. And that means the gravitational tidal forces acting across this moon are much greater. So, I mean, the force of gravity on the front of the moon is much greater than the force of gravity on the back of the moon. And that causes the moon to distend into whoopee, into an oblate spheroid. So you're basically taking your moon and you're squeezing it into a football shape. What happens is the moon has a natural rotation. In fact, let's try to draw this on the board here, because I think we could use some help. Let's take some notes so you have something to remember this by. Io. Most volcanically active thing, it's a moon, but even if you compare it to planets, most volcanically active thing in the solar system. And if you were to ask why, it gets a method of internal heating from a concept called tidal friction, with Jupiter. And the concept I'm describing here is tidal friction. And go through the thought process with me. Here's big old Jupe, mean and gravitationally intense. And here's little wimpy Io sitting next to it. Now I'm exaggerating the footballiness, but you're squeezing it into an oblate spheroid, so it's warped a little bit in the direction of Jupiter. But the moon also has a natural rotation to it. So as the moon moves in its orbit, now the principal axis, which you might call the major axis or the football axis, is no longer pointing at Jupiter. And do you know what Jupiter says? Jupiter says, hey, screw you, man. I'm tidally squeezing on you. And the moon then tries to deform and bend back in the direction of Jupiter. That's the equivalent of like kneading pizza dough, where you're smushing and warping and twisting the rock. And as you squeeze it and warp it, you add frictional forces that heat up the internal rock. Eventually it becomes so warm that volcanoes start popping off. Extremely thin lithosphere. So tidal friction causes internal heat from gravity warping the rock. And by the way, I do mean rock because the average density of Io is about 3 grams per cubic centimeter. So it's way more rock than it is ice. Most of the ice you see is in the form of that sulfur dioxide frost. In fact, today in our homeworks, we're going to be studying an interesting phenomenon related to the moons of Jupiter. Not only do the moons suffer from tidal friction, which heat them up, but the orbits of the moons also have a remarkable property where their orbital periods are whole integer ratios of each other, a phenomenon known as orbital resonance. Io completes exactly 4 orbits for every 2 orbits of Europa for every 1 orbit of Ganymede. And that's such a remarkable thing, it almost seems like evidence of design in our solar system. In fact, nothing could be further from the truth. When these moons began their lives and when they were formed, they probably did not have such interesting, remarkable relationships between their periods. Over the course of 5 billion years, natural resonance tugs caused by gravity have synchronized the orbits of these moons. And because we're going to do this in our homework and because this would have been part of our labs, I'm going to do a little kids break, a little mini quest here, where we pause EO and we just talk about the phenomenon called orbital resonance. I'm afraid if I don't do it now, I'll forget to get back to it. Oh, let's make one more mention though. An interesting part of EO having so many volcanoes is this. Despite the volcanism, there is no substantial atmosphere. And this on EO. And this is kind of a confusing bit here. Normally, atmospheres are created by volcanism. And with so much volcanism, you'd expect there to be some layer of gas around the moon. It turns out there's 2 reasons why there's no substantial atmosphere. The first reason is that it's cold and the gases tend to freeze to ice and basically snow down onto the surface. So the gases freeze to ice. And the word is deposits. The ice deposits on the surface. The second reason is even more crazy, and it has to do with the fact that the planet Jupiter has an immensely powerful magnetic field. Not only does Jupiter have an immensely powerful magnetic field, but Jupiter rotates wicked fast at 11 hours or 10 hours to complete a single rotation. What that means is that Jupiter's magnetic field is just zipping past Io every 10 hours and whacking the planet with a very potent magnetic field line. Now, I want to show you a picture. Do you guys remember a few years back, there was that really intense volcano in Iceland that broke through the ice, and it kicked up a cloud of sort of dust that caused airplanes to be grounded over Europe for a while? I'd like to tell you the name of the volcano, Iceland volcano, but the reason I can't tell you the name of the Icelandic volcano is because its name is this. Okay. Ija Falajula so-called. I don't know. Does anyone speak Icelandic and think they could help me translate this here? I do believe that there's a YouTube of an Icelandic guy who tries to do the pronunciation of that. So let's have a little linguistics break here. Okay. Since I can't pronounce.
So they can at least try to pronounce it right. So here it goes. It's Eyjafjallajökull. That's Eyjafjallajökull.
Eyjafjallajökull. Okay. There's Eyjafjallajökull. I can't really do it right. Okay. So this volcano, I mention it because I saw a picture in the New York Times one day while I was having my morning toast that completely blew my mind. And it blew my mind because there were these wild lightning bolts just shooting all throughout these volcanic eruptions. And I had to take a moment and I had to think about this. This is one of the photos that I saw. Now, the reason this picture blew my mind is it had never occurred to me before that volcanism would be associated with lightning activity. I did not comprehend the idea, why would an active volcano be creating its own lightning bolts? And then I sat there and I thought a little bit about it. Class, what do you guys know about lightning? Why does lightning happen as a phenomenon?
Something about electrons.
Yes. It's an
It moves
imbalance
from
of
an
charge.
area of positive to negative.
Yeah, but it starts with the clouds, right? So how
Basically
lightning,
static electricity.
basically all those water vapor clouds pushing through your atmosphere tends to remove charges. So what happens is the clouds lose electrons because they have friction with air molecules. And the clouds can build up a lot of positive charge. So much positive charge that the ground gets pissed off and basically sends a sizzling bolt of electrons from the ground up to the cloud to balance the charge out. Oh yeah, Andrew's saying that wildfires can create lightning. I believe it as well. So when I was thinking about this, I'm thinking, okay, just friction between clouds and the atmosphere is enough charge dispersion to create powerful lightning bolts. And then, of course, this Icelandic volcano made so much sense. Can you imagine the pressure and the friction of all of this gas being forced through a sheet of ice and then up into the atmosphere? Those gases must be pushing against air molecules with such violence that bits of electrons are getting chipped off of things left, right, and center. And of course, there's going to be potent electricity bolts because you're creating charge imbalance by the violence of gases pushing against one another. Once you've got that concept down, now go back to Io and realize that some of the gases that are blasting off of this moon, they must also be charged. And what's going to happen when Jupiter's wicked intense magnetic field comes zipping past this thing? It's going to collect those charges in the magnetic field, and it's going to rip them right off of the planet. But those charged gases will collide with neutral gases, and basically it'll help rip your atmosphere off your planet. And instead, all of those ionized gases become part of a ring of charged particles known as the Io torus. You'll remember that last class I told you that there's a consistent current of 1 million amps flowing back and forth between Io and Jupiter because of those charged particles that are being ripped off of it. So that's the second reason why Io doesn't have an atmosphere, is because the Jovian magnetic field is tearing off the charged particles, and that probably causes collisions with neutral particles as well. So the second idea is that the Jovian magnetosphere sort of rips them off to create the Io torus. And the Io torus is a buzzword because that's an interesting phenomenon. I found that interesting. I thought you guys would find that interesting.
So I've seen recently that they're saying that Mount St. Helens is like developing a glacier, or it has a glacier on top of the mouth of the volcano. So do you think that, yeah. So with that, with what you just told us, do you think that we could see that if Mount St. Helens erupts anytime soon?
That sounds reasonable. Mount St. Helens is really, I think, is that the one that's very close to Seattle? That's what's so crazy.
Yeah, that's the one that erupted in 1980.
Yeah, and like the whole city can get covered in ash. If there is a big glacier on top of there, it wouldn't surprise me if something like that is possible. So if you were a resident of Seattle and that sucker really had a major eruption, it would probably be terrifying because the skies would be covered in dark ash, and there'd be like these powerful lightning storms, and soot deposits would be coming down. You'd feel like you were in some nuclear fallout movie, you know? In fact, you kind of would be, right? So it would probably be quite terrifying.
Can I say something on that?
Yeah, please.
When glaciers, when they form in the empty cone of a stratovolcano, when they erupt, it will actually melt the ice and it will create a mud flow for anything below it.
Wow. So add mudslides into that mix is what you're saying.
Correct. So
if I was a tiki
they
bar
call it
operator,
lahars.
this is a real opportunity for some entrepreneur to start a tiki bar in Seattle called the Erupting Volcano, and they could have frozen mudslides and all kinds of different fun drinks. You can drink your way through the apocalypse there.
Yeah.
Okay, so anyways, let's talk a little bit about orbital resonance, because it's part of our homework today, and it's one of those things that you wouldn't think of yourself. You have to have an astronomer tell you about this, but it makes sense once you hear about it. I'm going to erase here, unless any objections are present. Okay, let's talk about a phenomenon that happens not only in Jovian moons, but also within planets in our own solar system. It's a concept called orbital resonance. And I'm going to define it in this way. Orbital resonance is a phenomenon where the orbital periods of either moons, or you will discovered, or planets themselves become synchronized into, and the key word is whole integer ratios, into whole integer ratios. And just an example, in case that doesn't make sense, whole integer ratios. Like, for example, 1/2, 1/3, 1/4, 2/5, 5/7, any kind of wacky thing is possible as long as you've got whole integers. Orbital periods of moons or planets become synchronized into whole integer ratios due to small gravitational tugs over time, over a long time. And I'm thinking 4.6 billion years time, okay? And let's just imagine how this would happen in a simple case with just a couple of moons, okay? Let's say you start with a planet, and then you've got moon number 1, and you've got moon number 2, and they just form completely randomly in our solar system with any old wacky periods that don't make sense. There is a collective gravitational force between the planet moon 1 and moon 2. And let's begin the relay race with all three in alignment, a syzygy, if you will. The distance between the planet and moon 1 is this red line, and the distance between moon 1 and moon 2 is this red line. Now let's have them travel on their merry way in orbit around the planet. As you can probably guess, the periods of these moons will not be the same. Why? Because p squared equals a cubed. The farther away you are, the longer it takes you to orbit the planet. So at some later time, moon 1 will be over here, and moon 2 will have only moved over here. Now consider the distances between moon 1, moon 2, and the planet. Instead of all being on a straight line, the distances are here, here, and here. Class, ask yourself, in which configuration will the gravity be the strongest? In the red configuration or in the blue configuration? Where will the force of gravity be greatest?
Would it be the blue?
No. The force of gravity depends upon mass, but also distance. The force of gravity is proportional to the product of their masses and inversely proportional to the square of their distances. So Frank, the blue would not be the stronger gravity. Why? Can anyone help Frank here? Does anyone understand what the hell I'm talking about?
Because with the red line, or the red example, it's a straight line. With the blue,
Well, this is a straight line too. I don't think that's good enough for me. That's a straight line, and that's a straight line. It's not that it's a straight line, it's that it's a line.
Collective force?
I'm sorry, Andrew, say it again.
Collective force of some kind?
I am talking about force.
Did you say collective?
He
Andrew?
said collective force.
Right, but that doesn't... My question was about the collective force. I said, in which configuration will the collective force be stronger, red or blue? You can't say the answer to that is collective force. That doesn't make any sense. I'm asking you, which one will be stronger and why?
Say red.
Why will the red configuration be stronger? I want a simple freaking answer.
Because the force only has to go one direction instead of two.
No, that doesn't make any sense. The force is always attractive. The direction of force is always attractive. They're trying to pull the moons together. There's a much simpler reason to explain why the force is stronger here and weaker there.
Is
The
there a
distance
line?
is shorter.
Yeah, because the fucking distance is shorter. The masses of the moons don't change. The mass of the moons here is the same as the mass of the moons there, right? That's not changing. The only thing that's changing is the distance. The distance is shorter there than it will be at some other time. Which suggests, Jake, that every time those moons are in alignment, you get a little extra squeezing. You get a little extra tugging. And try to imagine how that works. Every time these moons are randomly racing around the planet, anytime they come into alignment, gravity says, I'm just going to hold you tight for a second. I'm just going to squeeze you a little bit more. And what do you think that will do to those periods over billions of years of every now and then give you a squeeze? If you give someone a squeeze, sometimes they'll come back for more. Sometimes these moons will want to stay there and just stay there a little bit longer than they would otherwise. And then suddenly, 4.6 billion years later, you're in a committed relationship. Your periods are synchronized, okay? And suddenly, all of those moons are now in resonance with each other, right? And you got to see that you would never, ever predict this if you just looked at the periods. And as a way of demonstrating this dynamically, this is how we do orbital resonance stuff. Let's look up the moon Io, and let's get its period to like 4 significant figures, which I believe Wikipedia should have for us. Okay, so, okay, so over here in the data table, guys, write this number down for me. The orbital period is 1.769 days. Okay. Okay. So the period of Io is 1.769 days. We did this in our labs this week, although we got it 42 hours. Now let's look up the period of Europa. The next moon that I want to talk about. And I've got to do this quickly because I'm kind of running out of time here. The period is 3.551 days. If I had just shown you those 2 orbital periods, you wouldn't have noticed there was any connection between them. You probably would have thought, well, that's random, and everything's random, and we just live in a big old random universe where nothing makes sense. Worship astrology, okay? That's the logic that some people have.
It's roughly 2.2 to 1.
Not roughly. It's freaking damn smoothly 2-to-1. Watch what happens if you take, Joel, punch those into your calculator and tell me what you get to 4 significant figures.
Uh, 0.4982.
That's really freaking close. Wicked freaking close to 0.5. And that means this is a whole integer ratio. You got to be able to recognize them of 1/2. It's easy to recognize 1/2 and 1/4, but there are orbital resonances that are tricky to identify, like 2/7 or 5/7 or something. And what we would say is there exists a 2-to-1, not a 1-to-2, but a 2-to-1 orbital resonance between Io and Europa. I'd like to point out something weird. It's 2-to-1, not 1-to-2, because Io, having the shorter period, completes 2 orbits for exactly 1 orbit of Europa. That's kind of tricky how that works. So if the ratio is 1/2, the moons have a 2-to-1 orbital ratio. If it's 1/4, it's a 4-to-1 orbital ratio. Okay, please do the homework. Remember, Frank, you got a deadline, right?
You got it.
Get it done later tonight or tomorrow and just put this class to bed, okay?
You got it.
Great having you again, Frank. Live long and prosper, and don't be a stranger, okay?
You got it. Peace, everyone.
See you, Frank.
Okay. But I've told you about orbital resonance. I feel good about that. Let me just kind of zip through some of the moons. I'm running out of time, and we're going to have to do, I only have like a few minutes left before we have to take our break and do our homework. Can I just like show you some pictures of the moons and talk about them? I guess the game is up. I really don't have time to, I like giving you notes so you can look back on this later and remember what you learned. Let's look at the next moon of Jupiter. If the first moon was this wild, crazy volcanic moon, Europa couldn't be any different. What you see here is a giant ball of water ice. Now there's rock underneath it, but the entire planet is covered in sheets of H2O, water ice, frozen solid. Yes, some of the surface has these red deposits. They're called tholins, I believe. They're a certain chemical reaction with ultraviolet light. But all of those things that you're seeing are ice sheets. I want to show you a new enhanced version of Europa. They should have a couple of nice photos here in Wiki. So this is like a better version of what we just looked at. All of those cracks that you can see are ice tectonics. Basically, tidal stresses and probably internal heating cause the ice to fracture and crack and then melts back into place and leaves a kind of oh, whoa, check this out, guys. This is cool. It's a little animation of orbital resonance. I wish I had that present. You can see they're flashing every time the two moons align with each other. I should remember to use that next time. That's kind of cool. Io, you can see here in comparison to Earth and the moon. Io is about the size of our moon. Probably one of the most interesting moons in the entire solar system. Look at this up-close picture. Look how beautiful. This is the kind of thing that really gets me going in the afternoon here. What's going on here? Well, at first people thought that this moon was too small and too cold for there to be any liquid water. But they discovered as they flew, excuse me, when they flew past during the Voyager missions, every time Jupiter's magnetic field came zipping past this moon, the moon would create an induced magnetic field that would turn on every 10 hours, the same period of Jupiter's rotation. And they realized that the only way that you could induce a magnetic field is if underneath this sheet of ice, there was a vast subsurface ocean whose total liquid water content was greater than all of Earth's collective oceans combined. In other words, This is not just a moon covered in ice tectonics, but we believe that there is a massive subsurface ocean underneath these ice cracks. Now, first of all, guys, is this a young or an old geological surface? Look how beautiful that is.
Young.
Extremely young. And you can kind of see why, Jake. What looks like were ancient craters, every time the ice cracks and fills with liquid and freezes again, it kind of whoopies and warps the craters. So they kind of look like scabs that are healing on your skin. The craters are getting mutated and destroyed by very intense ice tectonics. Now, I have a little animation of how this might work, but this one shows you what's going on there. We believe that underneath this ice, and by the way, this ice is thick. It's like 5 to 10 kilometers thick in most places. That's deeper than the deepest ocean drilling wells can go, right? But they believe if you can drill down 5 or 10 kilometers through this sheet of ice, the tidal friction with Jupiter probably warms up enough of the interior of the planet to form these kind of hydrothermal vents or underwater volcanoes, which provide enough heat to warm up the ice and melt it into a liquid. Now, in our own deep ocean floors, hydrothermal vents often contain communities of organisms which are divorced from the solar food chain. So if you take a trip to one of Earth's hydrothermal vents, we find these organisms. They call them hydrothermal vent communities. And examples of these organisms would be the beautiful giant tube worms that you can see here. Basically, this is from Earth's mid-Atlantic ridge, and you can see this kind of underwater volcano going on. By the way, the temperature of the water here, despite being at the ocean floor, is boiling. The water is literally boiling like the kettle on your stove. And you see these giant tube worms and these small microorganisms and translucent crabs. There's all kinds of wild stuff to see down here at a hydrothermal vent community. If life can form in Earth's oceans using the energy of these hydrothermal vents, just imagine what could have been percolating down underneath Europa's ice for the last 4.6 billion years. It's entirely feasible that there is a whole ecosystem of marine life which has never been able to peek its head through the ice sheets and see the light of day. But they would have energy from the hydrothermal vents, and they could be swimming around in some kind of Darwinian arms race, and probably that stuff would be pretty wild and cool to look at. Now, no spoilers, but that cool movie I told you about, Europa Report, is about them going there and making the first mission to drill through the ice. And let me just say, things get a little bit exciting once they put their submarine down in there, okay? So check that movie out if you want to get the willies. People think that it's more likely for us to find extraterrestrial life on Europa than on Mars, because Mars is basically frozen and there's no more liquid water present. But here you have liquid water plus a heat source, and that seems to be the recipe for life, you know? Just to show you a couple of the other moons before all my time runs out. Once you go past Europa, you get to what is the largest moon in our solar system, Ganymede. But what do you guys see here in terms of the surface features? How is this different than Europa? This is also ice covering this giant moon here, but this ice is different how?
Well, I was going to say it has a good amount of cratering.
Exactly. And what does that tell you, Jake?
That it's much older.
Exactly. This ice isn't cracking and mutating and deforming as much. And it's kind of interesting. This moon's even bigger than Europa, so you would think it would have more possibility for, you know, internal heat, right? But we see that just like in our own solar system, the further away these moons get from the mass of Jupiter, they tend to be a bit colder because there's less. Remember that the force of the tidal force falls off very, very rapidly with distance. So Io gets a lot of tidal friction, Europa gets a little bit, and Ganymede's hardly getting it all. So the moons have older surfaces the farther and farther you get from Jupiter. Now, I should tell you guys that there is a debate in the scientific community. There are some planetary scientists who argue that there could also be a small layer of liquid water underneath Jupiter's ice. But it's clear to everyone that this ice is a lot older and hasn't formed any of those cracks and vents. The usual concept, or the usual theory, the dominant one, is that this is just a ball of ice with some lump of rock in it, but it's ice all the way down to the rock, and therefore it's very unlikely to be a source of living organisms. And when you leave Ganymede and you go out to Callisto, watch how this changes. Oh, by the way, one of the legendary features of Ganymede is the so-called grooved terrain. This shows that in the past, there were ice tectonics like you see on Europa, but that they have frozen out. Just like Mars's geology kind of froze out, the ice geology of Ganymede has frozen out and died off. Despite being the biggest moon in the entire solar system, it's not the most geologically interesting. And by the way, watch what happens when you go one more moon out into Callisto. How does Callisto compare to Ganymede?
Even older.
Even older. The story for this one is it's just a cratered ice ball. It's a dead cratered ice ball. I'd like to point something out. Do you guys see how all the craters are bright and white and shiny? That's because the surface ice is probably really dirty and covered in black soot from kicking around in the solar system. But every time a new impact crater smashes into the ice, it throws up fresh ice, which is shiny by comparison. So you can literally see the fresh ice underneath the old dirty ice, which is kind of cool. So if we go out to Saturn, we see something very different in its largest moon. And I'm just going to kind of talk about this quickly, and then we'll do a little pause here. I wish I had paced myself a little better today, but I was having fun. Unlike Jupiter, which has 4 big-ass moons, Saturn has 1 big-ass moon, which is Titan. But Saturn has something that Jupiter doesn't have, which is a plethora of what we would call medium-sized moons. And it turns out that these medium-sized moons play a big role in replenishing the icy particles that make up the beautiful ring system of Saturn. So the fact that Saturn has rings is related to the fact that it has a lot of medium-sized icy moons. But first, let's talk about its big boy, Titan. Titan is unique among the moons of our solar system in that it's the only moon to have a substantial atmosphere. Here we can see the moon at, I think, infrared wavelengths, where you can actually look through the cloudy atmosphere. And what does that look like down there at the bottom to you guys? This is going to be part of our homework assignment today. What does that remind you of? What do you think that is?
Is that a scarp?
Nope.
No.
It reminds me of like those I forget the name of them, like the things on the moon.
The Maria?
Yeah.
This is something even different than the Maria. Guys, that's a lake. That's a giant lake or an ocean. It's not an ocean made of water, though, because it's much too cold, 10 AU from the sun, for water to condense into liquid. That's an ocean of methane and ethane. It's basically methane at the condensation point, and they have lakes of liquid methane. The atmosphere is also interesting in that it's 90% diatomic nitrogen, which is quite similar to our own atmosphere. Our atmosphere is 77% nitrogen. So Titan has a weird connection to Earth. Its atmosphere is a cold-ass version of ours, minus the oxygen. We actually landed a probe on the surface of Titan during the Cassini mission. We were so excited to get down there because we had never seen another planet before that had an atmosphere with a liquid surface and possibly some kind of a waterway system like Earth. So although we knew it was going to be cold, the possibilities of interesting and complex chemistry were tantalizing. The mission only had enough battery life for 1 or 2 orbits, and famously one of the antennas died and we lost about half the images. But this is what we saw when we dropped down onto it. We designed this thing so that it could float like a rubber raft on lakes of methane and ethane. And during the descent, You can see them traveling 150 kilometers above the surface, 30 kilometers, 8 kilometers. This is a fisheye lens looking north, south, east, and west. What kind of geology can you guys see going on here? What does this stuff look like to you?
Mountains.
Yeah, mountains. And what kind of geology causes mountains on Earth?
Volcanism.
Yeah, which suggests that there might be some plate tectonics. You know what else these things look like to me? These look like those yardangs that we looked at during our lecture on wind erosion. So it's clear there's some tectonics here. There's also some erosional processes. And the legendary picture from the surface is of these frozen methane balls. So do you see these? These are basically snowballs of methane covering the surface. I'm not saying it's a beautiful world. Well, I am saying it's a beautiful world. It's just a lot colder than you'd have on Earth. But you do have some interesting similarities where you have liquids, you have mountains, you have erosion, you have lakes and oceans, and they actually detected methane rain. There was moisture on the ground from a rainstorm that had recently passed. Probably if you wanted to imagine what it would be like just from those pictures, let's get some help from our weed-smoking artist friends to draw us some space art here. Let's see, Titan, and let's just look at some fan art or some space art of what a day on Titan would look like to you if you could land your spacecraft there. It would probably be something like this, okay? This is, in fact, there's a couple of different art pictures like this. And let's grab this. Yeah. Or this. So if you were to go to Titan, there would be this hazy, smoggy, yellow nitrogen atmosphere. You'd see Saturn big and beautiful on the sky. There'd be all these mountains and lakes of liquid methane and ethane. You know, ethane is quite similar to gasoline, right? You could actually probably power a research base. Well, I guess you'd have to bring your own oxygen. That's the real problem. And there would be this complex waterway system made of ethane that served the same role that water does on our own planet. Could there be some weird frozen ice mosquitoes or some kind of interesting complex chemistry? Who knows? We still have this whole thing to explore, and we didn't get to do enough of it. So I'm looking forward to future space missions there. Okay, I've busted my time budget, and I have to be respectful of that. I didn't get to talk about Triton. I'll leave that up to your own Wikipedia investigations. Why don't we take a pause for 15 minutes or so, and then we'll crank out the homework. Does that sound good, everyone?
Sounds good.
Okay. I'll see you in a few minutes. All right. Let's get to it. It's our final homework. We'll make it a good one. We'll try to make it a quick one if we can. Jake or someone, or Joel, can I get your help with the numbers? I know it's chapter 11. I know that much.
47. Are you ready?
Oh, sorry. I'm
No, sorry.
a little slow on the draw today. 1 second.
Unacceptable.
Honestly.
One of the few times I do a movie reference. Don't ask me what it's from, but
I'm sorry. What's that?
I said unacceptable.
Unacceptable. Gotta get my act together. So in the usual style, we'll do name. We'll do AS1010. And I believe, is this homework number 11? Is that where we're at? And it's chapter 11. Okay, hit me.
47, 52, 54, 55, 57.
Okay. And Jake, chapter 11, number 47, we'll have you read that.
All right. Minor ingredients matter. Suppose the Jovian planets' atmospheres were composed only of hydrogen and helium. With no hydrogen compounds at all, how would the atmospheres be different in terms of clouds, color, and weather? Explain.
So there's only hydrogen and helium gas, no hydrogen ices, and they want to know about clouds, color, and weather. Okay, so why don't we look at Jupiter for a meditation point here? There's the clouds of Jupiter. What if Jupiter had just been pure hydrogen and helium gas? How would it be different? What do you guys
Well,
think?
it wouldn't have,
Jake?
it wouldn't have the yellowish or the reddish clouds.
No. So, okay, goodbye yellow clouds, goodbye reddish clouds. What about the white clouds?
I don't think it would have those either.
Yeah, geez. So what would it have then?
Good question.
So we remember from our lectures that the clouds are made of various different hydrogen ices, including water, right?
Yeah.
Remember, we dropped a probe into that bad boy. We talked about this last time. You had ammonia clouds in yellow, red clouds, ammonium hydrosulfide, white clouds are water, so these are all gone. So what would Jupiter look like then?
Would you just see the surface?
There is no surface,
Oh, that's right.
right? They're just balls of gas. Or there's no,
Wouldn't it?
huh?
So would it cease to exist?
Well, it would still
You
be
just see
there.
the core?
No, you wouldn't be able to see down to the core. The gas would be too thick. I guess the question is like, what does hydrogen or helium look like, right? At standard
Clear.
temperatures and pressures, let's see here. This is what helium gas looks like. What's helium gas look like?
It's colorless.
Yeah, hydrogen is too.
Yeah.
So wait, would the planet be transparent? You think it would be like invisible? Invisible planet. Nah, it wouldn't be invisible.
Be clear.
Well, at low densities, it's certainly clear. At some point, the gas gets dense enough to condense into liquid and maybe even solid. So you couldn't see through the planet like it was glass. But it would probably just be gray. It would just be a gray featureless ball with nothing at all. Just imagine a dull gray sphere. That's what it would look like. Except hazy at the edge.
That's boring.
Exactly. Would there be any clouds? No. Would there be any color? No. Could you have weather?
No.
Yeah, because there'd be nothing to condense. No ammonia drops, no snowflakes of water or something, right? Basically, 98% of Jupiter, Joel, remember that even today, 98% of Jupiter is in the form of hydrogen and helium gas. And what that means, and this is true about life too, 98% of the material is boring. What makes it interesting are the weirdos. The colorful weirdos, the 2% hydrogen ices, give Jupiter all of its cool characteristics. If you took away the weird stuff, it would just be a gray featureless ball. Let's write that down.
Well, when you said there wouldn't be any weather, I mean, there'd still be weather. Like things would still be happening, but you wouldn't be able to see it.
Think about what weather is, Joel. When you think of weather, you think of precipitation. You think of rain. You think of snow. You think of hail. What's all that shit made of? Water. But there's no water anymore. There's no ammonia. So what are you going to have weather from? The hydrogen.
Well, I mean, the stuff like weather happens to make the clouds do what they do. So like,
but clouds are made of water, Joel. If you take away the water, there is no weather. It's just a clear sky. When it's a clear sunny day, you don't consider there to be weather. You consider it to be a balmy sunny day, right?
yeah, but that's still weather though, right? Technically, yes. I mean, aren't there still be winds and stuff to affect the?
I mean, the planet would be rotating, so there might be wind. What is the definition of weather, anyways? You know, things that you take for granted. Oh, wait. Geez. The state of the atmosphere at a place and time as regards to heat, dryness, sunshine, wind. The weather, okay, well, whether or not you think of clear skies as weather, I think the point is there probably wouldn't be any precipitation or snow or rain.
Yeah, you wouldn't be able to perceive that there's weather going on.
Yeah. By the way, what about those convection cells? They would kind of disappear, right?
Yeah.
So it would just be kind of weird. Like, I think this is the idea. If Jupiter lacked all hydrogen ices, and was entirely comprised of hydrogen and helium gas, there would be no interesting features that contribute to its iconic what's the word I'm looking for?
Characteristics? Presentation?
Attributes? I don't know.
Appearance.
Appearance, thank you.
Yeah, good job, Jake.
Yeah, thank you. I'm good at English, not math.
I needed some help there, I was struggling. There would be no clouds, no banded stripes, no great red spot, no clouds, no banded stripes, no great red spot, no weather. And here we're excluding a clear hydrogen sky from weather. That's okay. Which Joel did somewhat successfully argue could be construed as weather, since it is a state of atmosphere. No weather. What was it? It was clouds, color, and weather.
Mm-hmm.
No weather, no rain, snow, probably no lightning. Jupiter would just be a gray, featureless ball, and probably be pretty boring to look at. Actually, you know what is a gray featureless ball is the planet Uranus. You don't really see much weather on it. Besides the fact that Uranus is green, if you've ever seen the old black and white images from the Voyager mission of Uranus, I mean, this is actually what Uranus looks like. Because it's covered in these sort of methane haze, you just see a green featureless ball. I wish we could get a more up-to-date, high-resolution picture to see if there was any microscopic details to the weather. You can almost see a cloud down here. Can you see that? You can just about make out a cloud. That's it. But this is what Jupiter would look like if it was just hydrogen and helium gas, except it would be gray.
So could we potentially see like craters on Jupiter?
No, because there's no real solid surface. You just get thicker and soupier as you go down into that.
Okay.
That's like saying, can you see a crater when you throw a rock into a pond? No, because the rock just sinks down into the water. You know what I mean?
Yeah.
You could make a crater if you threw a rock off of a building into the dirt, but not if you throw it into a lake. It just kind of sinks down into the bottom.
That makes sense.
Let me make sure everyone's got a chance to get the, oh. Okay, Mateus, I got your message. Okay.
Brendan.
Yes.
Sorry, I stepped out for a sec. If a meteor did hit like Jupiter or Uranus or something,
it probably does.
Would it just like, would you just see it like disappear almost? Like, would it just go through the?
Dude, I'm gonna do you one better. I've got a story for you. In the 1990s, the Shoemaker-Levy comet fractured into 20 pieces and rained down into Jupiter's cloud tops. And we actually captured it. Pretty much every major telescope in the world all pointed at Jupiter in anticipation of that event. Do you want to see some pictures of what it looked like?
Actually, yeah, I don't know.
It only takes a second. Dude, it made huge mushroom clouds. Like, imagine giant atomic bombs going off in Jupiter's cloud tops. Some of the mushroom clouds were the size of planet Earth. I'm so glad you asked that question, because that was supposed to be in my slideshow. Actually, no. So back in the day when I used to go through things faster and more efficiently, I actually had other lectures to give. For some reason, I've gotten worse over time. I've gotten slower. But since you're willing to talk about that, let me show you this. This is a picture of the Shoemaker-Levy comet. Keep in mind, we're looking at it from far away, and I think maybe in the infrared here. So you can just see that the comet kind of did a close encounter with Jupiter, and then the tidal forces ripped the comet apart. And here they are. They're all, you can see the shadow of Io on Jupiter. And do you see all those dots? Here they are heading for Jupiter. There's the first detection of an eruption. Okay. This is taken in the infrared. You can see these massive disruptions in the clouds. And look at that. It's hard to understand what's going on there, but that is a mushroom cloud the size of planet Earth. And as Jupiter rotated, the comets went pelt, 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 and they all kept striking it in different locations. So Jupiter was rotating and its clouds had all these giant mushroom cloud explosions. The heat from it was immense. It also helps us understand something that we see on the moon. They're called crater chains. And why do you see so many craters in a row? Probably because it fractured into a whole bunch of rocks. And as the moon rotates, they all splatter down in different spots. So these were some of the pictures of this. These are the only ones that I could find a few years ago, but I bet there's some better ones available on the internet now. I haven't updated that slideshow for a while. Shoemaker-Levy 9 Jupiter. And let's just see, because it's a very interesting question, and it just so happens that we have, so it looks like the pictures that I had were about as good an image as you can find out there. Yeah. So I guess I got all the best ones. Oh, actually, did you guys see that there was a video there? Come on. I don't know if this is a quick thing. Let's see if we can see the real-time rotation. At 10 hours, it's not going to look that fast, right? We don't have 10 hours to watch this video, obviously. I was hoping we'd see a sped up version of it. Whoa, that's cool. Look at that. What?
53,000 Fahrenheit.
Yeah, that's probably the temperature. Oh. Some of this is cheesy graphics made by art students, but whatever. It gives you a sense of what's going on. Yeah, I was hoping they'd show a real time. So you can see the resolution isn't as high as you'd like, but I mean, it would have been cool if that happened during the Galileo mission. Anyways, very cool question. And it just so happens I had an answer for that ready to go, you know? All right, can I erase this, everyone?
Oh, I'm not done.
Oh, sure, take a second. Yeah, so basically, it would be like dropping an atomic bomb. You know, a problem I never got to do with you guys, Noah, is I had a problem where we calculate the kinetic energy of a typical asteroid traveling at maybe 15 kilometers per second or so. If you calculate the kinetic energy of like a garden variety, maybe 10-meter asteroid, it packs the equivalent power of something like over 1 million nuclear bombs. So,
Brendan,
yes.
is that lighting or lightning?
Lightning. Sorry, that's lightning.
Okay.
So yeah, so it's basically like nuking Jupiter 1 million times over. You know what I mean? Very, very potent power to those impacts.
All right, I'm all done.
Are you good, Bella?
Yes.
Wonderful. All right.
That's insane. That's not the answer I was expecting at all, honestly.
Remember, you collide with gas, there's still going to be a lot of friction there. That's why those rockets need heat shields when they come into our atmosphere. The faster your velocity, the more friction, intense friction you're going to have. Okay, Noah, why don't you do penance here and read us number 52 if you can.
Take me 1 sec just to get it up.
Yep.
All right. Disappearing moon. Io loses about a ton of sulfur dioxide per second to Jupiter's magnetosphere. A is, at this rate, what fraction of its mass would Io lose in 4.5 billion years?
Okay, so let's pause for a second. A ton, a metric ton is 1,000 kilograms. So they're telling us that just from volcanoes, remember the story today, the volcanoes are going off and then the magnetic field is flying by and grabbing those gas particles and ripping them off the moon. And you're losing 1,000 kilograms per second. And the question is, if you're losing 1 metric ton every second, is that going to threaten to just emaciate the moon and just chip away at its mass? So the question is, if we let this go on, did they say for how long? 4.6 billion years?
4.5.
Okay. So we're going to let this happen for 4.5. How many zeros are in a billion?
9.
Right. And that means this is just a straight up dimensional analysis problem. The mass lost will be the rate of loss times the time. It's kind of like distance equals rate times time, except this is a rate of mass loss. We should convert them into the same units. So we have 1,000 kilograms per second times 4.9 billion years. And then we need to do a unit conversion right in the problem to convert from years to seconds. I don't suppose anyone remembers how many seconds are in a year, do you? Pi times 10 to the 7th seconds per year. So 1 year is 3.15 times 10 to the 7. Why don't you guys punch that up and tell me what you get?
It's 4.5 times 10 to the 9th, pardon, not 4.9.
Yeah, I don't know why I did that. And this is part A, so let's label this part A. Hey, let me give a message to any the night students out there. This is our last lecture, and it just occurred to me that the night students, I don't know if they have any last minute questions or anything, but feel free to send me an email if you're watching this later and you have any last minute questions about the class.
You want 3 sig figs?
Let's do 2. What we got? Joel?
Say it, Jake.
Oh.
1.42 to the 20th.
Times 10 to the 20th. What are the units?
Kilograms per year?
Hold on. Year cancels with year there.
Oh. Kilograms?
That's right. That's the kind of mass law. Now, the question is, 10 to the power of 20 kilograms sounds like a lot, but what percentage of EO is that? The mass of EO, let's just grab it off of Wiki. Let me cut down on this a little bit. Is 8.9 times 10 to the 22 kilograms. So can you guys tell me by dividing what percentage of EO's mass has been lost for the last 5 billion years? Well, hey guys, don't expect me to do this. This is your job. How do I figure out percentages? Please tell me you know how to calculate a percentage so I don't have to freak out.
Divide loss by EO.
Yeah, so do it.
Multiply by 100.
Exactly. Sounds like a great idea for you guys to do.
Is it 0.002%?
Wait, percent or decimal? What are you giving me?
Oh wait, no, that's the decimal.
So 0.002. So
yeah, and then multiply by 100. Yep.
So 0.2%.
Yep.
In other words, you don't even lose 1% in 5 billion years. All right. Ooh, I just got a little shock. I got a little static charge there. Part B.
That's crazy.
Yeah, that's not that much. Well, on the other hand, well, yeah, it's getting close to 1%, I guess. Sort of.
Oh, did you want me to read part B?
Yes, please.
Suppose sulfur dioxide currently makes up 1% of Eo's mass. When will Eo run out of this gas at the current loss rate?
Okay, so first let's just take 1% of Eo's mass, right? 8.9 times 10 to the 22 kilograms times 1%. Basically, that means 8.9 times 10 to the 20, right? Does that sound good?
Yeah.
Now, this is the total reservoir of sulfur dioxide. That's the mass of sulfur dioxide. And we're chewing through 1,000 kilograms per second. So we're going to do 8.9 times 10 to the 20th kilograms, and we'll divide it by the mass loss rate, 1,000 kilograms per second. In bidimensional analysis, that should cancel the kilograms and leave us with seconds. In other words, the time is the mass divided by the rate. Oh, I guess we don't need a calculator for that either, because we're just going to take away 3 zeros, right?
Yep.
8.9 times 10 to the 17 seconds. And we should probably convert that to years. I know that the number of seconds in 1 year is 3.15 times 10 to the 7. So how many years until it burns through its SO2?
$30 billion?
Really? 30 billion? I believe it, I guess.
8.9 is 9, and then 3.15 is 3.
Yep.
So that's 3, and then 17 minus 7 is
You're right.
10.
Now, hey, you're starting to sound like me, Joel. Very good.
It's numbers. I'm good with numbers. Jake's good with English. We put us together, we're geniuses.
All right. I like it. I like it. Good class. 30 billion years. In other words, if you've taken my stellar astro class, the sun is only going to live another 5 billion years. So pretty much Eo will never run out of sulfur dioxide. It will be swallowed by the red giant sun before that happens.
Crazy.
There was a part C, right, Noah?
No.
Oh, that was it? Cool. All right, another one bites the dust. I'll just give everyone a second to catch up to me. Andrew,
Yeah.
can I erase?
Yeah.
Joel, you want to take on 54 for me?
Yep. So Prometheus and Pandora.
Oh, this is really interesting exercise.
These two moons orbit Saturn at 139,350 kilometers for Prometheus and 141,700 kilometers for Pandora. use Newton's version of Kepler's third law, find their orbital periods, and find the percent difference in their distance from Saturn and in their orbital periods.
Okay. That's part A, right?
Yep.
All right. This is kind of an intense problem. I don't think you guys will get this unless I show you a picture of what's going on here. Prometheus and Pandora would definitely be in the small dirtbag moon category of moon. But there's a reason why Prometheus and Pandora are interesting. And I didn't get to explain this today. The reason why is they're an example of what are called shepherd moons. And shepherd moons are little tiny moons that are buried inside the rings of Saturn. And they achieve two goals. They do two things. They sometimes call them gap moons, but in this case, here's a picture, an actual image of Prometheus and Pandora. Not only do they contribute to the icy particles that make up the rings, but the shepherd moons actually serve as little gravitational shepherds, which herd icy particles into rings like the F ring. So the F ring is a bunch of collected little icy bits that are kind of gravitationally nudged into place by Prometheus and Pandora. You would think that Prometheus and Pandora are close to each other because their distances are just a little bit away from each other. But what you're forgetting about is being close in radius does not mean you're actually close. And that's because there are small differences in the period that will cause one moon to drift away from the other one, and they'll actually spend most of their time on opposite sides of Saturn, only very rarely and very occasionally linking up. This problem, although it's a bitch, will aim to show us why. I'm going to try to speed this up so that it doesn't take quite as long by doing a lot of the dimensional analysis for you. So let's very quickly convert these things into meters, right? As you know, let's do Prometheus first. I'm going to label them Pro and Pan. And I'm going to start by writing down the equation for NK3. And I'm going to substitute the numbers right in so we can get to business. So P is the square root of 4 times pi squared times the distance in meters, which will be 1.39. Wait, did they give it to that many sig figs? Did they say 139,350?
Yes.
Whatever. It's not necessary, but 1.3935, 1, 2, 3, 4, 5, 6, 7, 8 meters. And that's cubed, divided by big G, which is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of Saturn. I got to look that up. To 2 sig figs. Saturn is something times 10 to the 26 kilograms. 5 times 10 to the 26. I was right. 5.7 times 10 to the 26 kilograms. Punch that up, guys, and don't make any mistakes. What you get? Say it loud, say it proud, Joel.
Okay. Let's see. 53,000.
Units?
Let's see. That's meters cubed, so that cancels.
Joel, make it easier. It's P. MKS units is P.
Seconds.
Yeah. How many hours is that?
Uh, 3,600 seconds in an hour.
14.7 hours.
Yeah.
Okay, that's pretty cool. Let's do Pandora. Same thing. .417 times 10 to the 8 meters cubed over 6.67 times 10 to the negative 11 times 5.7 . I was a little lazy. I didn't write down the units of G. Sorry. That's bad form, but who cares? Well, anytime now, guys. I'm going to grow old and die here. And I'm already old. So I'm just going to die. Looks good, Bella. 54,350 seconds. How many hours is that? .0 hours. Oh, sorry, 15.1 hours. Okay. Let's talk about how to do percent difference, okay? So up here, the percent change in distance is the change in distance, delta R, divided by the inner radius. So that means we've got, and let's do this once again in kilometers for a second. I'll need to erase this. We had 139, sorry. We had 141 700 kilometers minus 139,350 kilometers. I think those are the values.
Yes.
And we'll just divide it by the inner rate. We'll divide it by the inner radius of 139,350 kilometers. Now, if I punch that in and leave it as a percent, is 2,000 parts divided by 139,350. It's basically 2% difference. 2% difference in orbital radius or orbital distance, however you want to say it. Meanwhile, the percent difference in the period is 15.1 hours minus 14.7 hours over 14.7 hours. So it's a 3% difference in the period. Their periods are similar and their distances are similar. That's the point. And yet, that does not mean they spend a lot of time near each other, ironically speaking. Can I erase this stuff at the bottom here?
Yeah, you can.
Okay. So, Joel, read me part B now.
Part B is consider the two in a race around Saturn and one Prometheus orbit. How far behind is Pandora in units of time? And how many Prometheus orbits will Pandora have fallen behind by one of its own orbital periods? Convert this number of periods back into units of time. This is how often the satellites pass by each other.
Okay, so this sounds crazy, but let's imagine Prometheus and Pandora going around Saturn. Let me try to draw this a little better. So first of all, here's Saturn. Okay. And first on the inside, we'll have Prometheus. I will call it Pro. And on the outer edge of the F ring, we have Pandora. I'll call it Pan. And I'm going to let Prometheus go once around Saturn. We know that takes 14.7 hours, right? Because it takes Pandora 15.1 hours, in 14.7 hours, Pandora will not have completed a full orbit, but Pandora will be lagging behind by some small amount of time. That change in time, delta T, the difference in time will be 15.1 hours minus 14.7 hours, which is 0.4 hours, correct?
Yes.
Now, the first time it orbits, it's going to lag by 0.4 hours. The second time it orbits, it'll lag by 0.8 hours because you're already behind by 0.4 and now you're behind by another 0.4. The third time, it'll be 1.2 hours. The time after that, it'll be 1.6 hours and so forth and so on, right? How many times will it take until it falls behind by one of its own orbits, it would be, take the orbit of Pandora and divide it by 0.4 hours. So 15.1 hours over 0.4 hours, and that will be a raw number of orbits.
$37.75.
So let's say 38 orbits.
And then you multiply that by 15.1?
Or do you multiply it by 14.7? Hold on, let me think about this. This gets
Let's see.
confusing.
And how many Prometheus orbits will Pandora have fallen behind? No, we already did that. Convert this number of periods back into units of time. This is how often.
They said how many Prometheus orbits, right?
Yeah.
The first orbit, you're behind by 0.4. The second orbit, you're behind 0.8. After 38 orbits, you are behind 15.1 hours, I think, and then you come back. But that's 38 Prometheus orbits. So weirdly, you've got to do 38 times 14.7 hours, right? Because each one of these loops is a Prometheus orbit, not a Pandora orbit, correct?
No, we calculated Pandora because the 15.1 is Pandora's.
Right, but it.
So yeah, we have to convert the 38 orbits to Prometheus.
We have to use Prometheus's time to convert it back into a unit of time.
Yeah.
So what's 30? That's very tricky. That's why this problem is kind of interesting. So can you do 38 times 14.7? What's that?
559
hours.
Yeah.
And I think it says, does it say that's how often they're going to line up with each other?
This is how often the satellites pass by each other. Yeah.
Right. So that's.
So every 23 and a quarter days. Yeah.
So basically, even though their periods are 15 hours and they're only different by 3%, they only line up once a month because most of the time they're spent on opposite sides of Saturn. It's kind of like if two runners are on a racetrack and they're very close, but one is a little better than the other, they actually won't be in the same part of the track at the same time very often because it'll take them a long ass time for them to synchronize again. So weirdly, the message of this story is kind of interesting. You don't spend the most time next to the planet that you think is closest to you. You spend the most time next to planets that have whole integer ratios of your orbits. There could have been a moon that was much farther away, but had exactly half of Prometheus's orbital period, and Prometheus would line up with it way more often because they have whole integer ratios or they have harmonic periods of each other. It's the harmonics that you line up with more often. And that's sort of a cool, surprising result. Was there any other part to that question, or was that it?
That's it.
Okay, cool. Andrew, let me know when you've got all that down.
I'm all done.
All right. By the way, I had to erase up there, but we were doing chapter 11. What were the 5 problems again?
47, 52, 54, 55, and 57.
And we've done 1, 2, 3 problems now, correct?
Yes.
Okay, Andrew, can you read us number 55?
Number 55, all right. Where is it? Orbital resonance. Use the data in Appendix E. Identify the orbital resonance relationship between Titan and Hyperion. And if the orbital period of one were 1.5 times the orbital period of the other, we would say that they were in a 3-to-2 resonance, which medium-sized moon is in a 2-1 resonance with Euclideans.
Oh, Enceladus. Okay, first let's get the periods of Titan and Hyperion. They say in Appendix E, but we'll just grab it off of Wikipedia because who cares? Hyperion moon. Um, 21.276 days. Shoot. 21.276 days. And now Titan, which I had up and I took down. $15.945 days. Okay, let's do part A. The name of the game for orbital resonance is you divide the little guy by the big guy and see what you get. Three sig figs will do for me.
.749.
Which is basically what fraction?
3/4.
Exactly. So we would say there exists a 4-to-3 orbital resonance between what and what?
Titan and
Hyperion. Titan will complete 4 orbits for every one of Hyperion's orbits. Sorry, Titan will complete 4 orbits for exactly 3 of Hyperion's orbits. Now, they're looking for a medium-sized moon that has a 2-to-1 ratio with Enceladus. And the period of Enceladus is 1.370 days. One thing I don't like what the book did is they're looking for a 2-to-1 orbital ratio with Enceladus, but they're actually looking for a 1-to-2 orbital resonance with Enceladus. Meaning, wait, hold on, is that right? No. I think we're looking for a moon with twice its period.
Which medium-sized moon is in a 2-to-1 resonance with Enceladus?
So we're either looking for something with an orbital period of 2.74 days, or if it's half, because I'm not sure what they meant there, we're looking for 0.685 days. Now, I've got the table here. Let's see if we can get this off the internet. Cosmic perspective, moon data. Does anyone have a digital copy of the book? You'd think I would, being the instructor here, but they're kind of chintzy about things. I wonder if I could sign in. Does anyone have a copy of the book? A digital copy? Hello? Can anyone hear me?
Yeah.
Does
I
anyone
have
have
a digital copy. I have the regular book.
All right, I got the regular book too. Fuck it, let's do it that way. Where's the regular book? I want to see if you guys can figure this out without my help. Ah, whoa, I almost sent you guys on a flying sleigh ride here. Here's the moon data. The third column is the orbital period. What do you got?
Dione.
And also Helen and Polydeuces. Isn't that interesting that there are like 3 freaking moons that have the same orbital resonance? Dione, Helen, and Polydeuces. Which one is the medium-sized moon?
Your camera.
Blurry.
Pardon?
It's
Oh,
Focus is
blurry.
off.
Yeah, wait. I was trying, okay.
That's better.
You know which one is the medium-sized moon?
Ion.
Yeah. You know, I don't know that much about Dione. Isn't that weird? Maybe every time I eat a snack, I should memorize the facts of a different moon. That would be probably more interesting than that garbage stuff I usually read. Look at those giant cracks. Some kind of ice tectonics there. Enormous canyons extending from mid-latitudes in the trailing hemisphere to the moon's south polar region. So this is the part that heads towards the sun around Saturn, and this is behind. That's interesting. Pretty big moon. Those definitely came after heavy bombardment. Oh wow, look at that. Look at that circular shape to the canyons. Very, very interesting. I'd like to read about this sometime. Okay, I won't keep us. We have one left to go, right? Was that the end of that problem?
Yes.
We're almost done, kids. The last one is a big doozy. You would have had to do pretty much this problem on your final exam. Is anyone taking the final? It doesn't sound like it. Hey, works for me. I'm going to erase, okay?
All right.
How about your other classes? Do you guys have a lot of stuff final projects due? Is anyone drowning in work right now? Or do you guys have it under control or what?
Oh yes, I am drowning in work with other classes.
Oh, really?
Same here.
Yeah.
Wow. So I bet not having that final exam was kind of a load off your mind, huh? So you could just
Yeah.
focus on
I
cleaning up the
forget.
other stuff.
I keep forgetting to do it.
Well, Cam, please finish up in good standing because you put in a lot of work in this class. So if you can get through this bullshit and come out of it passing your classes, you'll feel pretty good. You just got a little
I
bit
think
more
it's
to
just
do.
we do this kind of work like this, and that's why I'm passing. If we didn't have lectures and we had to do homework on our own, then I probably wouldn't get an A or a B in here.
Yeah. You know, that's one of the reasons why I'm probably going to have to do this again and run the hamster wheel next semester because, well, there are some students that can do it. Like I noticed in the night class, maybe about a quarter of them or so didn't do anything. So they're in trouble. But there is a number of people in the night class who came home each night and they watch these videos and they turn them in or whatever they're doing, they're getting their stuff in. So if you
I did that when I had to leave early a few times to go to work. I've done
right. If you stayed very, very disciplined, but I have to admit, oh, Ava, you only need to email me if you are doing the final. I am going to presume that for all of my students, none of you want to take the exam. That's probably a good assumption. If there is someone out there that does want to take it, then they should email me because they're going to be in the great minority. All right. Otherwise, I'll be trying to field emails from 120 of you guys and it'll get all messy. Kevin, it's okay if you didn't.
Brandon, why don't you just send them like the video for the lecture and then do like Zoom for the homework with them?
Because there's only so many times a day I can repeat myself without going crazy. You know what I mean? Like I've got plenty to do grading papers and stuff where, oh, I see. Oh, for next semester, you mean?
Yeah. No, not now. Next semester. So like, you send
trust
them the
me,
video
don't
for
give me-
lecture.
I haven't made up my mind how I want to do that. Yeah, I could just do the home. You know why? I'm afraid they won't actually watch the lectures. That's why. I'm afraid that I need psychological peer pressure to I don't know. I'm still wrestling with it, Bella. I got a month to think about it. Definitely, I'm going to find some way to make everybody happy. So,
well, Brendan, I would say if you're gonna do Zoom for anything, you have to do it for the whole thing because I because I have a class at 11:30, so that's why I usually come in late.
Mm-hmm.
And I've had to be very disciplined and kick my own butt to make sure I watch the lecture, because otherwise I just do the homework and say, screw it.
I could see that temptation. I'm sure if I was a student, I would totally have that temptation. I'm sure a lot of night students are doing that. It's sad because I think there is some value to listening to the lecture. Okay, Jake. That's okay, Jake. I should get two things because Jake is going to die here. But I guess my only point is...
I'm going to stay on as long as I can.
Okay, Jake. I think next semester I might try to start it at noon. But okay, let's get to biz before Jake dies. Anyone wants to chat afterwards can. Jake, did you read us a question yet?
I read the first, but I can read this one if you want.
Yeah, sure. Let's just get through it.
All right. Titan's evolving atmosphere. Titan's exosphere lies nearly 1,400 kilometers above its surface. What is the escape velocity from this altitude? What is the thermal speed of a hydrogen atom at the exospheric temperature of about 200 Kelvin? Use these answers and the method of Mathematical Insight 10.2 to comment on whether the thermal escape of hydrogen is likely to be important for Titan.
Okay. We have a hydrogen atom at 200 Kelvin. I wrote down the mass of a hydrogen atom. Let's draw the picture. So here's Titan. Titan has an atmosphere. The radius of Titan, I think, is, oh gosh, what's the radius of Titan? The mass of Titan is 1.3 times 10 to the 23 kilograms. The radius of Titan is 2,600 kilometers. This is a little bit of a long-winded problem, so I'm going to try to do I'm going to do it as fast as I can for Jake's benefit. Please draw this picture. We have a sole hydrogen atom, and it's threatening to undergo thermal escape from the exosphere of Titan, which the book points out is 1,400 kilometers above the surface. We're going to calculate the escape velocity first in part A. The escape velocity is the square root of 2g mass of the planet over the radius plus the height in meters. And I'm just going to do the conversion to meters real quick because probably no one gives a shit, and that'll help Jake. So really quick, the square root of 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared times 1.3 times 10 to the 23 kilograms. Let's see, 2,600 and 1,400 is exactly 4,000 kilometers. And in meters, that's 4 million meters, right?
Yes.
So why don't you all punch up and get me the escape velocity in meters per second.
I got 4,550,000.
I think you forgot to square root it.
Oh,
Yeah,
I
you
did.
Yep. Wow, that was quick, Jake.
You know,
So what'd you
getting
get
it
this
finally, last day of class.
What'd you get once you square rooted it, bud?
So 2,133.
Can someone else confirm that?
Wait.
Yes.
Oh, thank God.
And that's meters per second, right?
Yes.
Which is 2.1 clicks per second. So that's the escape velocity. Okay. Andrew, let me know when you got that done because I'm going to have to erase to do part B.
All right.
All right, I'm erasing everyone. Shout at me.
Thankfully, I was able to write that down before you erased it.
What?
Thankfully, I was able to write it all down before it got erased.
Wait, you were or you weren't?
I was.
Oh, okay, good. Good, thank you. That's why I said to shout at me. Okay, now for part B, we're going to calculate the thermal speed for hydrogen. The thermal speed equation is the square root of 2 kT over the mass of your particle, where K is the Boltzmann constant. The thermal speed then is the square root of 2 times 1.4 times 10 to the minus 23rd joules per Kelvin. The exospheric temperature is 200 Kelvin. And for some crazy ass reason, I have the mass of hydrogen atom memorized. It's 1.67 times 10 to the minus 27 kilograms. So let's punch that up and see how our thermal speed is looking. And now a word from our sponsor, Polar Seltzer. When you're traveling through the atmosphere of Titan, you might get a bit thirsty. Nothing like a delicious can of Polar Seltzer to keep you sailing above those methane seas.
I got 1,831.
Okay, so let's call
Man, you're on fire, Jake.
Yeah.
It's on fire.
1,800 meters per second, or 1.8 kilometers per second. If you compare this to the escape velocity, remember that the escape velocity was 2.1 kilometers per second. If the thermal speed of hydrogen is 1.8 kilometers per second, can the hydrogen escape the atmosphere of Titan?
No.
Jake, you would be wicked wrong.
I just did 2 good math things, so it counteracts.
Okay, it's true. But I don't blame you. It looks, Jake, like it won't be able to escape, right?
That's the thermal.
The thermal speed. But remember, the thermal speed, remember that gases obey a Maxwell-Boltzmann distribution of velocities. Say what? What the shit are you talking about? I'm talking about not all the gas particles travel at exactly the same speed. Remember that the gas particles at the thermal speed is the most likely speed. We calculated this velocity here, but there are a number of gas particles that will occupy the high-speed tail. The question is, how does this number compare to the escape velocity, and are they more or less than a fifth of each other? That's the test for atmospheric loss. So Andrew, do you have all this down? I need to erase. Cam, do you have all this down?
Hold on, I just need one more thing.
Yeah, I still need to write it down.
Sure. Why don't you let me know when you guys are done?
I'm all done.
I'm still writing.
All right, Cam, let me know.
All set.
Awesome. So last little bit of business here, and there's a cool moral to this story. Okay. Apply the test. And it's the test for atmospheric loss. Is your thermal speed greater than or equal to 1/5 of the escape velocity? The thermal speed was 1.8 kilometers per second, which is clearly greater than 1/5 of 2.1 kilometers per second, which equals 0.4 kilometers per second. So Jake, while it looks like the thermal speed isn't quite at the escape velocity, there's going to be a shitload of gas particles which are moving well above 2.1 kilometers per second. Therefore, the hydrogen, pure hydrogen gas, can escape Titan. And believe it or not, while that might sound pretty boring and dull to you guys, this is the cause of the liquid ethane lakes. Now, hear me out for a second. You guys know that one of the most abundant hydrogen ices in the outer solar system is the molecule methane. And methane is CH4, which is one carbon with 4 hydrogens stuck to it. And despite the lie that I told you earlier today, methane, even at the temperatures that you would find in the atmosphere of Titan, methane is not heavy enough to condense into a liquid, and methane would be in a gaseous phase up in the atmosphere. But now check out this bad boy. Along from the sun comes some solar wind or some ionizing UV radiation. So from the sunlight, we get some very high energy ultraviolet rays. And what the ultraviolet rays are going to do is they're going to knock off and chip off one of the hydrogens. Class, what will happen to that hydrogen once it's been knocked off of the methane molecule?
It'll escape.
It'll achieve thermal escape. And what will be left behind? What will be left behind is a carbon with 3 hydrogens. Now, imagine that carbon with 3 hydrogens bumps into another carbon with 3 hydrogens. They will then combine to make a new, much heavier molecule, C2H6, otherwise known as ethane. C2H6 is the much heavier ethane molecule. And because ethane is so many times heavier, it will condense into big liquid drops, which then rain down onto the surface. And before you know it, you have an ethane lake. So the thermal escape of hydrogen explains how ethane forms in the atmosphere and then rains down to form a lake. Isn't that cool? And this is why lakes have formed on Titan. So just add one note. This helps form ethane lakes. For Jake's sake, we won't get any more long-winded than that.
It's on battery saver, so we're touch and go.
I just wanted to make sure you got to the end so you didn't have to wait 3 hours to watch the video all over.
Thank you, I appreciate it.
Yeah. I think that's kind of a cool story. The first time I learned it, that was like an aha moment for me, you know? All right. Well, guys, and gals and humans of all stripes. It's been a real pleasure tiptoeing through the solar system with you this semester. And despite this shitty virus that's trying to control our lives, we hunkered down, we got our work done, and we learned some things. And we got one more semester of this madness at least. So we're going to have to get used to it if we want to learn. The alternative, which I would argue is so much worse, is sitting around for a year or two doing nothing and then having to start over. You want to make sure that when you come out of this, you can be ready to have your degree in your hand and get some kind of an interesting job or whatever you're trying to do. Go to grad school or anything like that. But I'd strongly recommend that you don't get psyched out and that you finish your degree so that you're in a good place when all this is over. You know, it's actually, in a way, it's hard to focus when you're at home, but it's also the best time. You've got nothing else to do anyways, you know? You might as well just sit down and do this hard stuff while there's nothing else going on. That's my 2 cents. Okay, guys. Thank you so much, Ava. It's been a pleasure teaching you. And you too, guys. So, hey, if there's anything else, send me an email. I'll be assuming that you guys won't, hi Greg, I'll be assuming you guys won't be taking the exam unless I get direct message from you. And I'll compute the grades by Saturday or Sunday, and it should be good for everyone, as long as those homeworks are in, okay? So just keep me in the loop on the concerns. Joel, you and I have each other's numbers, so we'll talk about maybe observing. Oh, last thing, the 21st, a couple of weeks from now, Jupiter and Saturn, as you know, are going to be really, really close together in the sky, 1/10 of a degree apart. So even if you don't have a telescope, I want you to look up on the 21st, which I think is a Monday, see if you can see Jupiter and Saturn close together. And who's ever in your COVID pod, your brother, your dad, your girlfriend, whatever, show them that and see what's up. If you have binoculars, take a look at it. Okay. Over and out, guys. I'll see you in the
Professor.
Yeah.
Bye.
Bye. Bye, everyone.
See you guys.